After this talk of consensus algorithms, our next guest will lead us to another fundamental aspect of blockchain, smart contracts. Bozhidar Nikolov is a developer at Quanterall, and he will present us how a virtual machine can be implemented for smart contracts. Give it up for Bozhidar.
Thank you. Just a second. So, hello everybody. As you already understood, my name is Bozhidar Nikolov, and I'm part of the Quanterall team working on Aeternity Elixir node. So, as you heard not long ago on Yanni's presentation, when he mentioned the various virtual machine versions and the contract languages that they want to support, on the bottom of his slide was the name of the Solidity language. So, as me and my colleague Nedelchev decided to do all the contract-related stuff, we decided that our first step was to build an initial virtual machine with EVM functionalities, which is designed to execute Solidity contracts. So, a quick overview. I'm going to talk about the virtual machine itself and what modules it uses to operate. There are basically several types of memories, the stack, the memory, and the storage memories. Next up, I'm going to talk about what limits the execution and how we provide some payment for the execution. That is the gas parameter. Next up are the virtual machine internals, which are generally the outside data that the virtual machine receives when it is being initialized. That is information about the environment in which it is executed, information about a transaction that contains the executable code, and information about the previous world state. After that, I'm going to go through what the bytecode is itself, how it is being executed, what are the runtime exceptions that can occur, what are the different opcodes and opcode categories, and I'm going to mention a few more complex instructions. So, first of all, what exactly is the virtual machine? It is a quasi-Turing complete machine, where the quasi-qualification comes from the fact that the limitation, as I said, is limited through an initially stated parameter, which is the gas parameter. And it is a stack-based architecture, which means that it uses stack to store internal operations, arguments, and results. And you hear the term word, and that refers to a 256-bit integer. And those will be the stack items of the machine, the storage keys and values, etc. So for the main components of the virtual machine, those are the various memory types. The first of which is the storage. So the storage is the memory of the virtual machine that persists on the blockchain after finishing execution. And for the internally, it is simply represented by key value pairs, each of which has a word size of 256-bit. But reading from and writing to the storage are quite expensive operations, so we have to keep that in mind when we use it. And it's important to know that every contract can only modify its own storage. The next one is the memory, that you can imagine it as a normal RAM memory, where it is some, in theory, endless byte array. It is not persisted on the blockchain after execution, and it is empty at the start of the execution, whereas the storage is derived from the previous state, if there is such. Reading from the memory can be done in 256-bit, while writing to the memory can be done in either 1 or 32 bits. And every time the memory expands during execution, we calculate new fee based on the current size of the memory. So in order to calculate the new fee, we have to use this formula here. So for the new fee, we have to calculate the fee based on the memory's old size and subtract that on the fee calculated onto the memory's new side. And the size of the memory is considered in 32-byte chunks. So if we have 33 bytes of allocated memory, the size of the memory will equal to 2. And finally, we have the stack storage, which is just simple stack storing words which are 256-bit in size. And the stack has a maximum of 1024 elements. And as you can see, instructions generally, most of them, pop some arguments of the stack and push some result back onto the stack. So one of the most simple virtual machine instructions is the add instruction. And what it does itself is it takes two arguments of the stack, do something to them, push a result back onto the stack, and in this case, this is perform an add operation between them. So what limits the execution? As I said, that's the gas parameter, which by definition is the internal pricing for running a contract. And of course, with the calling transaction, which must provide some amount of gas. And during execution, the gas is being gradually used by the virtual machine according to specific rules. And when an out of gas exception is being triggered, which could be a pretty normal case, all changes made during the execution are being reverted to the caller state. So the virtual machine internals, as I said, the virtual machine upon initialization receives some data from the outside world. And first, it receives information about the environment in which it is executed. And that's information about the current block and previous blocks. So we have the current block's difficulty. We have an instruction for that called difficulty. We have the current gas limit of the block, the current block's number, current block's timestamp, and previous block's hash as well. It also receives data information about the transaction that contains the executable code. And as you can see, that is the account of the address under which the code is being executed. We have the address of the execution's origin, address of the execution's caller. We have the value of the call, or in some cases, the nation of a create operation, if we have such. We have the code, the actual code that should be executed, and this is not the code that is associated with this account in the previous state. We have the gas price, which is a parameter that implies how much gas price does 1 unit of gas have. So the creator of this transaction initially must pay amount of gas multiplied by gas price. And gas is the total amount of gas provided for the execution. And there is an instruction called gas, which returns the current amount of gas left. And finally, the virtual machine receives information about the previous world state, which is a set of the pre-existing accounts prior to the execution, their state prior to the execution. And the previous world state is mapping between addresses and accounts. And accounts, of course, hold balance, its nonce, its body code, and again, its storage that's associated with this account. Again, mapping of keys to values. So how is the bytecode being executed? The bytecode first is just a sequence of bytes. And each byte stands for an instruction which is called an opcode. And usually opcodes are followed by optional parameters. So most often the bytecode will be represented by hexadecimal values. And here we have a pretty simple example of a bytecode. So 1 byte will be represented by 2 digits. And as you can see, we have 3 push operations, 1 add operation and 1 mstore operation. So the push operations simply take the next number of bytes from the bytecode, they take it as a value and push it onto the stack. So first we're going to have 1 push instruction, which will push the value 1 onto the stack. We'll have a second push instruction, which will put value 2 onto the stack. Then we have the add instruction, which, as I said, pops 2 arguments of the stack and pushes their added value back onto the stack. So in the stack, at this point, we're going to have the value of 3. Then we have the third push, which will push the value 32 in decimal, which is a pretty convenient memory address. And then we have the mstore instruction, which takes two arguments of the stack, one referring to an index in the memory, and the second one is the actual value that you want to write. So, as I said, the bytecode is being executed sequentially, and it is done instruction by instruction. And there are instructions that manipulate the order of execution, either by directly changing the value of the virtual machine's program counter, or reading the next n values, n bytes as a value, which are the push instructions that I mentioned. And on every instruction execution, certain amount of gas is being subtracted from the initial gas provided. So, what are the runtime exceptions that can occur? Of course, there are such. The most convenient one is exception running out of gas, that is trying to spend more gas than we have left. Another one is an operation trying to take more slots off the stack than they're available on the stack, or push more than 1024 elements, stack underflow and overflow. And another one is jumping to a bad jump destination. That is because the only jump destinations in the bytecode are the ones labeled by the jump destination opcode, and determining them requires pre-processing of the bytecode, so that we don't, because there are some trick situations like this byte shouldn't be inside of a value of a push instruction, and so on. And finally, we can have an invalid opcode, like someone has passed some unsupported byte in our code. So for the opcodes themselves, each has a predefined count of items that it pops from the stack, and predefined items that it pushes back onto the stack, and as well how much gas they consume. And most of them take arguments of the stack and push back some result back onto the stack, but there are some that take no arguments of the stack and still push some result back onto the stack, like for an example, instructions like gas or PC, which push onto the stack the value of the current gas and the program counter, respectively. And number of opcodes take arguments of the stack that refer to positions and sizes in memory. And those are instructions like call, create, return data, etc. And SHA-3, which I'm going to show you later. So the opcodes are being divided into the following categories, each of which is represented by a hexadecimal value, starting from 0, and mostly every category contains 16 bytes in total, except for the push operations, which are 32. So for the first category, stop and arithmetic operations, those are the most basic ones, I would say. Here we have instructions like stop, add, subtract, divide, etc., where stop is the controlled halt of the execution. And it's important to note here that all the division operations of division, side division, modulo, and modulo, if they have a dividend of 0, the result will be 0 from that operation, and not the divider argument itself, like in most programming languages. Next, we have comparison and bitwise logic operations. Those are operations like less than, greater than, and binary and, or, etc. Next up is the SHA-3. And here we have just this instruction, the SHA-3 instruction. This is the only crypto instruction in the whole virtual machine. And what it does is it takes some address that refers to the memory and how much bytes to read from the memory, and makes a hash of that array part and pushes it back onto the stack. Next up is the environmental information. That those are opcodes that provide access to all the environmental data that I mentioned above, together with some instructions that provide access to external accounts codes. Next up, we have block information, which are instructions that provide data for the current block. And we have the stack, memory, storage, and flow operations. Those are instructions that obviously provide some access to the internal virtual machines modules. So for the stack, we have simply pop and push operations. For the memory, we have mload to read from the memory at a given address to read a full word at a given address. We have the mstore8 and mstore, and the difference between that is, as I said, the mstore8 stores just 1 byte, and mstore stores a full 32-byte word to the memory. For the storage, we have simply sload and store, where you keep a full word at a given key, or you retrieve a word from a given key. And we have the flow operations. Those are the various jump-related instructions. So next up are the push operations, which are 32 in total, and they are named push. Pretty convenient. And what they do is they take the next number of bytes from the bytecode as a value and push it back onto the stack. So for example, the push1 operation will take the next 1 byte from the bytecode and push it as a value. Push2 will take the next 2 bytes and push it as a value, and so on. The next 2 categories are simply stack-related categories used to duplicate and swap elements on the stack. So each of them is 16 in count. So the duplication operations are named dup. The dup1 operation will duplicate the first stack item, the dup2 will duplicate the second stack item, and so on. And the exchange operations are called swaps. So the swap1 operation will swap the first and second stack item, the swap2 will swap the first and third stack item, and so on. Sorry. Yeah. Next up are the logging operations. Those are opcodes that are used to create log entries, which are to be utilized for outside of the blockchain, and they are special index data structure purely to provide some information and cannot be accessed directly from the contracts. And finally, we have the system operations, which are the most complex ones. Here we have the creation of account, call of another contract, return of some data, and so on. And as I mentioned, the system operations are the most complex, so I'm going to take a moment and dig deeper in some of them in order to show you how there are some dynamic calculations based on the runtime. So for the call instructions, we have 4 of them different. So the normal call instruction is to call from your account with code associated with your account. The call code instruction is call from your account with code associated with another account. The delegate call is the same as a call code, but persists the value of sender. And the static call is the same as a normal call, but the call value is set to 0. So what these call instructions do is they create a new instance of the virtual machine, each of which has a fresh memory of stack, program counter, and memory. So, but they work on the same balance and storage as the parent call. So the result from a call instruction is either 0 or 1, depending on whether the execution has been successful or not, whether there has been a runtime exception thrown or not. And this result is, of course, pushed onto the stack. And an interesting rule is that a call instruction can only consume 63/64 of the current gas, for example, and it can have an additional 9,000 gas cost, for an example, if the transaction value is not 0, and 25,000 more if the destination address does not yet exist. And besides that, the child call can receive a stipend of 2,300 gas if the transaction value is not 0, and that is typically done so that the child call would always have gas to log that it received funds. And after execution, any excess gas is being returned to the caller. So for a simple demonstration, I'm going to show you a very simple Solidity contract that has some persistent variable called x, and it is an integer. And this contract has 2 functions. One of them is add function that takes 2 parameters, performs an add operation between them, and store them in this variable x. And the second function is to retrieve this persistent variable. So this contract in its function part translates to this bytecode here. And I know this doesn't talk to you much. What I'm going to show you next I hope I clarify just a bit. And now I want to remind you about the data parameter that the virtual machine receives, because we're going to use it in the demo, and basically the data parameter is used most often to provide some pointer like to a specific function from the contract that you want to execute, and to provide parameters to that function. So this contract, if we disassemble the bytecode, it will look like this. So up to line 13, we kind of extract the first 4 bytes from the data parameter, which is a part of the hash of the signature of the function. So we just pass the first 4 bytes, and as you can see here and here, we check if it equals to one of those hash values, and if it does, we jump to a certain instruction. So if this is for the add function, this is for the get function. So if we have passed the value corresponding to the add function, we will jump over here, which is a jump destination, and this here is basically the body code of the add function. And if we have passed the value corresponding to the get function, we're going to jump over here, and this here basically is for the get instruction, I'm sorry, and this here is for the add instruction, for the add function. So I'm going to demonstrate to you real quick how first we're going to call the add function, and we're going to see how in the storage we're going to have the value that we want. But as our contracts are not stateful, they're not yet stateful, I will simulate this process by hand. What I mean is I will import by hand the previous state of the. Now I'm going to show you what the data parameter looks like. So this is the state of the virtual machine, the initial state of the virtual machine. I haven't populated some real data because I would not fit it in this whole screen, unfortunately. So I'm going to show you the data parameter. So we're looking at the white part here. So as you can see, binaries in Elixir are represented like that, like byte values with these triangle brackets surrounded around them. So as you can see, the first 4 bytes will correspond to the add function that we want to call. And as I mentioned previously, the virtual machine works with words, which refer to 32-byte values. So we have instructions to read from the data passed to the virtual machine at a given address to read a full word. So after these 4 bytes corresponding to the add function, we have another 32 bytes of the value 3. That will be the first parameter, and another 32 bytes of the value 6. So basically, we will perform an add operation between 3 and 6. And now if I execute the virtual machine with this state, we should see in the storage that we have the value 9. And in the normal scenario, this value will be persisted on the blockchain after the execution, but in our case, it's still not. So I will show you a bit, step by step, how the execution is being done. So here in our virtual machine, it works internally with just integers, normal integers. So as you can see, up to here is where we derive the first 4 bytes. So up to here, we have this integer value that corresponds to the 4 bytes that we have passed in the data parameter corresponding to the add instruction. So here we check whether we've passed we check if those two equal. This is for the other instruction, for the get instruction. Here we see that we don't match this. The result from the equal operation is 0. So this jump is conditional jump, and based on this value, it only jumps to this instruction if this value is 1. And since it is not 1, this is not the function that we passed. We check if either. This is the function that we're looking at. So this is the function that we're looking at, and we push the number of instructions that we want to jump to. And since the result from the equal operation is 1, we make a conditional jump to instruction 49. And here, this is the program counter. Instruction 49 is the actual jump destination instruction, so you won't see it. And as you can see, the instruction 50 is a push instruction, and here we push an address corresponding to addressing the data parameter, and then we say call data load, like from the 4th byte, give me the full word, that is the value of 6. Then we say again for the second parameter the same thing, and then we just say add, and we have the value of 9, and then we store it in the storage at a given index, and that's it. We say we're ready with the execution, and we jump away at the stop, which is all the way somewhere in the beginning of the program. And so that's it. We executed the add instruction. Now I'm going to show you. We'll execute the get instruction as well. The get function. So the virtual machine's parameter that sets the output message from the call is called out. And now, if I inspect it, we should see some bytes, and we should see that they correspond to the value of 9. Sorry, typo. Yeah, and as you can see, it corresponds to the value of 9. But again, our contracts are still not stateful, so I kind of imported with this dummy. This is the dummy address for the contract. And here in its storage, it has the value of 9. And so that was it. Some questions? I will be happy to answer considering the virtual machine. Yes, we have a question. You can say it, I'll repeat the question. Yes, exactly. That's just some. So the question is if that's some code that just can be executed by some parties. Yes, that's exactly what it is. It just lives on the blockchain under a given account, under a given address, and you can call it, and it has an internal state, as I showed. So yeah, was that a question? Yeah. Dispute in what manner? Well, the question was, how do they dispute about an agreement on the contract, about two parties having an agreement on the contract execution, and I would say that this is simply related to the contract itself. It should handle such cases, and yeah.
Are anybody else required or supposed to execute this contract to confirm it for the other parties, or just the two parties execute?
No, they just execute it and store it in the blockchain. That's it. The contract initially is being created through a transaction, so it is already verified in some way. So yeah, once it is there, you can call it based on some rules, of course. But yeah, no problem. Some other questions?
Hi.
Yes.
So you mentioned internal virtual machine. Could you expand about it?
Say again, internal virtual machine.
Yeah, you mentioned that.
I probably mentioned initial.
Initial.
Yeah, initial. Oops. Yeah, initial. I mentioned initial because even the Solidity-related virtual machine is not yet ready. For example, we don't have the account creation instruction yet. So yeah, there is still some work. That's why I mentioned the word initial. Yeah.
And another question is, so there are virtual machines to execute different kind of parameters. There's the Ethereum virtual machine. Well, do we have other Ethereum, like cryptocurrencies virtual machines?
Yeah. Well, it is simply for Solidity, if I understood your question.
Yeah.
Yeah. Simply for Solidity. Yeah. It's just a virtual machine, and in theory, you will be able to run anything on it, but you just have to compile it for it. Okay, thank you for having me.